3D-IC for the masses. Advanced assemblies have enabled an unprecedented rate of the advance in the data center, especially for neural processing, but can it expand beyond that? The concept of 3D-IC and chiplets have the whole industry excited and potentially marks the next stage in the evolution of the IP industry, but so far, technical difficulties and costs have curtailed its usage to just a handful of companies. Within those, they do not appear to be seeing benefit from the heterogeneous integration or reuse. Attempt 2 is making this happen are not new. A decade ago, we were trying to create an architecture for building a chiplet. And says Mark Kermer is Vice President of the Technology and CTO of the Custom Solution and Marvel. We have a noble goals that were very democratic about being able to define a structure where people could put a multiple chiplets together to build a given function. The magic was that by putting these smaller chips together, as we could use the much less power-hungry interface, we could take what to use to be a big power-hungry, complex and extensive system and build it into a chiplet-based system that could be more efficient overall. More importantly, it would save tons of development cost and save a lot of our chip cost. It didn't turn out that way, and we ended up with a scenario where just a small number of companies which you can count on your fingers had the capability to develop the chiplet. So why do it? One of the things big drivers is an increasing amount of content that is vital but not differentiating. The mass market is still a few years away from the stop adopting 3D-IC, but there's applications where it's well suited, and the US government is very focused on those applications, said Lachishi Kamer, director of the Central Engineering Solution at Siemens EDA. It makes a lot of sense. You think about the 6G wireless communication because your antenna pitches are sharing to the scale where you can think of an array patch antenna within the package. You would have the antenna array patch at the top of the package. Then you would have an array of the power amplifier circuitry. You'll have a beamformer circuitry beyond that, and you enter into a digital domain where we have the data processing and connectivity to your baseline computer. There is a lot of modularity emerging into the market. People are starting to look at new architectures, and so corollary today, they are also thinking about how they can enable the mass market. In the past, companies pushing for a technology have funded the necessary research and development, which then tricked down to the masses. Industry leaders are gonna be first with his advanced new technology, and the broad assumption as the industry will follow, said Mark Twinen, director of the product marketing at ANSYS. But there is a growing gap between the two, and the two front of runners have outpaced the field and are pulling ahead of the mainstream. They worrying about the theme. That is the still general belief that a 3D-IC or a 3.5D will become the norm as the system gets larger, especially if the chiplet market takes off. But as these gaps grow, it opens up the potential for competitive displacement. You're 2 or 3 years behind competitors that has mastered this technology. Suddenly you get serious differences in marketing positioning. Put simply, there is a big separation between those that are adopted to stay competitive and those who wish to adopt it. So chiplets enable us to more cutting-edge stuff, and is allowing us to put a lot of silicon on a package, which is helping us to scale performance, said Marvel's Kumar. As we need this because, as everybody would agree that we have significant slowing of the mover slow. This is not the only reason to want a 3D-IC. However, 3D-IC technology offers numerous benefits, including increased performance, low power consumption, and main miniaturization, said the Rosaria Baker, the field CTO for Rapidus Design Solutions. Rapidus adoption spans the various applications for mobile to high-end users like AI, supercomputers, and data centers. The technology ability to enable compact design with improved performance continues to attract interest. Still, significant challenges remain. Most of the people using 3D-IC are vertically integrated, said Ansis Swinen. There are bigger companies that have the wherewithal to design the chips, design the interposer, and simulate the whole thing, and look at the package and go through the many architectural choices that have to be made. It's complicated and remains a degree trailblazing. So, large chip or small PCI. 3D-ICs are not just about shrinking everything on a PCI. For different benefits, people tend to swap the comparison baseline, said Sweden. That's not really fair. The PCB gonna a smaller system. PCB going to a smaller system. That was the SoC. If you worried about getting better performance than your PCB and you go to an SoC, that is a natural evolution. It's what we've doing for 40 years. The disaggregation to the multiple chiplet is not because you're trying to be compact a PCB. It's because it's trying to make take what was monolithic chip and you are disaggregating it, disaggregating it. The comparison baseline is a monolithic chip, not a PCB. But not always. Early success stories such as HBM bring more external components into a package. With the increased need to bring in more functionalities within the package, it has become more difficult to achieve that using monolithic SoC type structures, said Rapidus, that is Baker. Baker. So not all functionality requires leading-edge designs, while the leading-edge design prioritizes the highest performance cores and smallest form factors. Such approaches may not be the most efficient way where the heterogeneity is important, and more functionality is needed within the system. Moreover, if chiplets were readily available, 3D-IC could be viewed as being a PCB within a package. The PCB really limits the amount of bandwidth that the chips can use to talk to each other, said Ramin Fajadurad, CEO and co-founder of Alien. It has only gone up less than 2 orders of magnitude over the past 20 years, compared to 5 orders of magnitude for a chip. This is major as contributor to the memory and I/O worth by moving the equivalent of a PCB inside a package, see figure 1, and the density of the boards, which we call bumps and micro bumps, goes up significantly. The distance between the chips goes down significantly. You can much higher bandwidth at much lower power between these sides. In figure 1, chiplets are the future of the semiconductor, says Alien. Continued monolithic advancement are being constrained by yield. People are hitting Recticle's limits, said Mayank Bhatnagar, product marketing director of SSG at Cadence. If you have a large piece of silicon that you want to build, that's just at the reticle limit, but much before that, you will start having yield issues. If you can't make it profitably, there is really no point marketing it at all. That is where monolithic dies, which are very large, are headed, so they are just become too large. The yield drops, and the drop is enough that it becomes uneconomical. So, doing everything on a leading node is not required. AI is demanding the more SRAM on die, and SRAM has it scaled, said Jimenez Kamal. Theoretically, you have the smallest SRAM bit in 5 nanometer, and then it starts to grow after that. If you look at the dollar per bit cell number, that stopped scaling way before the 5 nanometer. Even though we were shrink though the 7 nanometer and 5 nanometer, and the bit cell side was coming at a higher cost of cost per bit. Two things are happening. You need more SRAM, the SRAM is more expensive, and 3D, just because of its closeness, almost zero latency interface between the two dies, allows you to experiment with different hierarchical and cache structures. So ideally, the best technology would be used for each component. We can build numerous chips in cutting-edge technologies, and the chiplets become a crunch to help us to do that, said Quemel. We are breaking things into more pieces so that we can cheat and get more silicon than we could have had in one integrated tape-out. We could ping-pong I/O technology with core die technology so that we can just push the envelope and use the best available technology, which usually tends to be the most extensive technology. We had these ideas before, and they didn't pan out that way. Some of it had to do with the reality of building a multi-chip system. The combination of the technology and development cost is driving more companies in this direction. With the latest process node, the cost per transistor is going up, said Cadence's Patnagaru. It doesn't make sense to transfer every part of your design into a new process node because most of the design may not benefit from it. If you have an RF transceivers or analog block, it will not benefit from the reduction in cost per transistor. On the other hand, you will have to redesign it for the new process node. When you disaggregate, you are able to move only the portion that benefit from a new process node. By the way, it sounds very anti-thing, but the reuse of previously designed chiplet in a new design is fraught with peril. The cost effectiveness. Where there appears to be a lot of price intensivity in the data center, AI has put such a premium on high performance, very complex, very large silicon system that it has been worth it for them to put in the huge investment to chase this market, says Sweden. They have a reason why they need huge 3D chips. It's the AI application, and until the technology becomes cheaper, all the other sectors of the market find their own killer application for 3D. It will be a slower go for them. The rest of industry is looking and waiting. When I talk to our mobile customers, I don't get the feeling they are ready for 3D-IC because the economics are yet making sense to them, said Camel. But at the same time, they understand they are hitting the limit of the scaling. They are getting small incremental benefits when moving from 5 nanometers, 3 nanometers to 2 nanometers, and this incremental benefit comes at the huge cost. The only reason they are going to these nodes is to get the maximum performance out of the transistor, and especially driven by the new transistor architecture with a gate-all-around GAA. But GAA is a very complex process. This is a low. The problem is twofold. First, they need to adapt a completely new design and packaging methodology. And second, they go from a single tape-out to multiple tape-outs. It might make sense of the company to be in the triplet style of design, said Elad Alon, the CEO of Blue Cheetah. That means they need a multiple market set. They are possibly need multiple tape-outs and the initial NRE to do that versus a large monolithic chip in an advanced node is tough to swallow, and the NRE required to get out of the order is likely to be lowered by sticking to a monolithic solution. It is complex dance, as is true of many things in engineering. What you would do in steady state. Once you've already got a large enough market and a large enough business, may be quite different to that as what you have to do to enter, because the considerations are different. There are several technical challenges that still need to be improved. When I think 3D right now, my mind goes to the hybrid bonding, because that's where you get the real bang for your buck, said the Kumala. It helps you resolve some of the thermal challenges. It gives you very high connectivity and very low power consumption that involve thinning silicon to extraordinary and small thicknesses and integrating copper to copper bonds at very fine pitches. When you look at the physical challenges of doing that with multiple suppliers, that becomes challenging. HBM is still to get that point. 3D memory is still only using microburns to connect the memory to the main die, it says. The memory providers are working on hybrid bonding approaches that we all hope will go into production in near future. When we'll look at doing this real cutting-edge stuff with multiple pieces of silicon, that's where it's gonna get really interesting. The eliminating the phi potentially adds a lot of performance. When you go to an almost phi-less architecture, you're talking of the very fine-grained 3D interconnect, very small interconnect, and they can be achieved today with a wafer on a wafer level stack, said Camel. If you go to the die on wafer level stack, the interconnect pitch is longer. And that's where I draw the boundary. You then need the special buffers, and it is probably a stretch to think about the phi-less architecture. Where the challenge with any 3D stack, you have the backside metal on at least one die. As soon as you fuse two dies, you still need to take IOs out. The power supply is out through the substrate. So the power density and thermal challenges are becoming well-known problems, but there's others to be considered. Let's say you have the front of band line, the transistor layer, and the die that has the backside metal to get IOs out of your die, explains Camel. Now you have a metal on both sides and transistor stack, and what happens as a result is your metrology becomes very challenging. If something needs investigating, you want to use X-ray photography or some kind of visual scanning, that becomes very challenging. Additionally, focused ion the beam uses the backside of silicon to go inside the die and making changes. We call it feeding in the IC. When we are trying to debug something and establishing a hypothesis for a failure in the die, you do some fits. You redesign your die based on your FIB experiment. Then you may remask and reduce the design. Now you have lost the ability to FIB from the backside if you design a chip and it doesn't function in the field. You have a very big gap in terms of debugging the chip. And heterogeneous stacking edge complications. Heterogeneous integration requires a combination of different technologies, both old and new, said Andy Heineck, head of efficient electronics and from Fraunhofer IIS Engineering of Adaptive System Division. A significant difference is the signal levels of older technology nodes. Newer nodes require much lower levels, while older nodes need higher signal levels. Achieving compatibility in this area is challenging. Often, only lightweight die-to-die interfaces are needed, as the integration of the digital IP is highly limited in terms of space in older technologies. Reuse adds more complications. For 3D, the biggest constraint is you want the two dies to match its size, says Camel. Otherwise, it wastes the area. You can do die-on-wafer integration, where one die is not quite the same size as the other die, you are losing out on how many dies you can process at the wafer level packaging or integration. There's a throughput challenging, but on one advantage as an architecture, as you don't have to be homogeneous. It can be heterogeneous. One die can be in 5 nanometer, the other in 3 nanometer. So, conclusion, 3D-IC had the potential to transform the IP and semiconductor industry, but it remains a very expensive option, which today is only applicable to the data center and even the only because of AI. There are many challenges that have yet to be overcome, and it would appear that the notion of 3D-IC for the masses is still something for future. Before 3D-IC can move beyond the vertically integrated companies, a lot more work is required on interface, standards, tools, and methodologies. This will be examined next month. Okay, today I read this article, 3D-IC for the masses. Thank you for your time. See you next time.